We welcome you in this final afternoon session of the Ctbuh Mumbai conference entitled Advances in Structural Engineering, Part 2. The opening presentation today of the session will be given by Cary Kopczynski. Cary Kopczynski and company, he's a CEO, his own company in Seattle, and he's going to give a presentation entitled Envisioning the Future, Building, Design, and Construction in the New Millennium. Can we please welcome Cary to the podium? Thanks.
Well, thank you, Chuck. And thank you also for being here. We hope to make it worth your while. My name is Cary Kopczynski from Seattle in Washington State, not Washington, D.C. in the U.S., the northwest corner of the country. And I want to talk to you today about a couple of things. First, the technology explosion that we're all part of. All of us in the business of architecture, engineering, construction know that in the last 25 to 30 years we've gone through a virtual transformation in the way we do our work, in the way we produce our documents, in the way we relate to the construction job site. So I want to talk about that, and then I want to talk about the latest aspect of the technology explosion, which is BIM, and the challenges, the opportunities associated with using BIM in our design offices. I want to illustrate both of these aspects of my talk with first some very old buildings, and then with some newer buildings that my office has been working on. But I want to illustrate this with first some very old buildings, and then some very new buildings. I think there's a tendency often for those of us in the design professions to assume that anything worthwhile, anything useful in our design office has been invented in the last 20 or 30 years. And that just isn't true. There are a lot of things that we do day to day, a lot of design techniques that we use day to day, whether we're structural engineers, architects, contractors, that have been around for a long, long, long time. So to begin with, I want to talk about a very old building. This is the Parthenon in Athens, sits on top of the Athenian Acropolis, completed in 432 BC. It's a wonderful achievement in architecture and engineering and construction. All of the stones were quarried many, many miles away from the city of Athens. They were brought in with very primitive equipment to the top of the Acropolis, erected with very primitive cranage. They're fastened together with nothing more than some metal staples, if you will, that are held in place with molten lead. And yet the building substantially stands 2,500 years later. The next building, this is the Lighthouse of Alexandria. This building, or tower rather, stood on the island of Pharos, which is just outside of Alexandria, Egypt. It was constructed by one of the Egyptian pharaohs in the 3rd century BC. It stood for almost 2,000 years. It finally toppled in about 1350 AD. Was about 125 meters tall, so almost 400 feet tall. They used to light bonfires in the top of this structure, and the purpose of the bonfires were to serve as navigational aids for the ships in the Mediterranean Sea. Now this building, or this structure rather, was constructed with what we now know as dry stone masonry. And what they essentially did is they built this structure with large blocks of stone that were very carefully chiseled to fit very precisely together, and they used no mortar. And what they had learned in ancient times is that when they built with dry stone masonry, that the buildings would tend to withstand earthquakes much better than if they used mortar. Now, we understand today the reason behind that. The reason is that if you fit together large numbers of stones or blocks, you fit them together very precisely, and then you load the building up with an earthquake, the friction that develops both in the vertical joints and the horizontal joints between those stones dissipates large quantities of energy. So when you build with dry stone, you essentially have an automatic energy dissipation system. And it worked very well, because the building was built in the 3rd century BC. It went through 21 earthquakes with only minor damage, and the 22nd earthquake finally in about 1350 AD knocked it over. But that concept of dry stone and building shear walls with energy dissipation is something that we try to emulate today. the Roman Colosseum in downtown Rome, the largest Colosseum built by the Roman Empire, would seat 50,000 people at capacity, was completed in about 80 AD. You notice the large wall at the top of the Colosseum, right above the third row of arches. What the Romans had learned is that if they pre-stressed or pre-compressed the columns and loaded the columns with large gravity loads, that they would tend to stand up in earthquakes much better. So part of the reason for what is known as the attic wall by a lot of scholars who study the Colosseum, that large wall on top, the attic wall was built to pre-stress or pre-compress all of the columns below. Because when you pre-stress those columns and then apply lateral load, you reduce the net tension. And since they didn't have steel, reinforcing steel to build with, they were interested in minimizing the net tension in the columns. And they did that with that large attic wall. And again, with respect to the Colosseum, it worked very well because it suffered virtually no damage until the same earthquake that toppled the lighthouse in Alexandria hit Rome in about 1350 and knocked down a portion of the Colosseum. But it stood for almost 1,300 years with very little seismic damage. The Pantheon in downtown Rome, we're moving through time here. This is about 125 AD when it was completed. All of the columns and the portico out front were quarried granite from Egypt. They were loaded on boats, shipped down the Nile River, across the Mediterranean, up the Tiber River into Rome, and then transported with carts to the site of the Pantheon and erected with primitive cranes. They weigh 60 tons apiece. They're unitized columns. They're one-piece granite stone columns, 60 tons each, and they were installed with the crane systems of the day, which is quite an achievement. That would tax a lot of modern-day cranes, a 60-ton pick. But the real majesty of the Pantheon is internal. The interior of the Pantheon, the dome, is still today, 2,000 years later, the largest unreinforced concrete dome anywhere in the world. It's unreinforced concrete. The compressive strength is roughly 20 MPa, which equates to about 3,000 psi. The oculus in the center is 27 feet in diameter that allows light to enter the interior. The building has been in continuous use since it was constructed, which, as I mentioned, was in 125 AD, so almost 2,000 years. They used a much denser aggregate down at the base of the dome than up at the top of the dome because they understood the importance of minimizing the dead load. They coffered the dome both for structural reasons and also for architectural reasons. The coffering reduced the dead load and then, of course, provided a very dramatic effect architecturally. There really isn't much we could do today if we went out to rebuild the Pantheon to improve it. And all of that was done with no reinforcing steel at all. And interestingly enough, a finite element model by some local university students was run on the Pantheon just a few years ago. And they ran a full FEA on the dome, and the highest tensile stresses they discovered anywhere in the dome were about 15, that's 15 psi. Almost no tensile stress anywhere in that unreinforced concrete dome. All of the Roman aqueducts in Rome alone, they built 500 kilometers of aqueducts. At the peak of the empire, they could ship or transport 300 million gallons of water per day. 300 million gallons of water per day could be shipped into or transported into downtown Rome. They were all built with stone, no reinforcing steel. Many of them still stand. This is San Gimignano in the Tuscany area of Italy. This was the high-rise community. Between the 11th and 13th centuries AD, 72 high-rise towers were constructed. About 15 of those remain today. The city was very wealthy. It was on a trade route. The people who ran the town became very wealthy trading with local communities and decided to spend their money building high-rise buildings, not unlike the motivation behind many buildings today. And they built 72 high-rise towers, 15 of which still stand. This is the Campanile Tower in downtown Venice, or in the San Marco Square in Venice. Constructed in about 1100 AD, suffered some damage in an earthquake in the 1500s, was partially rebuilt, and then spontaneously actually collapsed in 1902. But it's 100 meters tall, very simple structure, stone and clay masonry. This is where Galileo actually made many of his observations of the heavens, from the top of the Campanile Tower. But it has been standing for nearly 1,000 years. It was rebuilt in 1902 in its original form, and for 1,000 years it has been a 100-meter tall high-rise building in downtown Venice. This building needs no introduction. This, of course, is the Taj Mahal, all constructed with white marble. In the mid-1600s, apparently about 20,000 laborers worked on this for a number of years. And then finally, the Empire State Building, one of the most iconic high-rise buildings in the world, completed in 1931, 3 months ahead of schedule. They had charted out an 18-month construction schedule. They completed the building in 15 months. They erected it 4 floors per week. The only unfortunate aspect of that was the building opened up in 1931, which was the Great Depression, and it didn't make $1 of profit until 1950. So it took 20 years to make some money for the owners, but it was the tallest building in the world until 1974, when the World Trade Towers opened up and eclipsed it in height. So what do all of those buildings have in common? Well, I think they have a number of things besides being, in most cases, very old. First of all, they all started out with very simple design concepts. Very simple, fundamentally sound design concepts that obeyed the laws of physics and mechanics, things that I think today sometimes with all of our technology get overlooked. As I mentioned when I started the talk, part of what I wanted to discuss today was the importance of keeping your eye on the ball, if you will, staying focused on the importance of starting a project with a good concept, because as we all know, a well-engineered bad idea is still a bad idea. A well-engineered bad building is still a bad building. And what I think all of the structures that we just looked at have in common is they started out with very good ideas. Now, did they have the computing power? No, they didn't have the computing power. A slide rule, which you see there on the screen, was a high-tech instrument in the day of most of those buildings. And that's the second thing they have in common. They started out with fundamentally good ideas, and secondly, they were analyzed and designed with very primitive tools. And yet they still stand and in many cases are still in service today. The same holds true of the way the documents were prepared. The drawings and the documents, such as they were that were produced to construct those buildings, were obviously drawn manually by hand. The tools that this young gentleman has in the photograph were probably pretty advanced when many of these structures were built. He has a T-square and a bottle of ink and a pen and some triangles and French curves. Many of those things are now in museums. They aren't used anymore. Everything is done these days, of course, with CAD. But there was some beauty in that, and there were some lessons that I think we should carry forward into our offices today and not forget. Many of you structural engineers, architects, building contractors can relate to the fact that today, if we design a building that 30 years ago would have taken 20 drawings to produce, today we might turn out that same job with 40 drawings. A job that we would have taken 30 or 40 drawings 30 years ago might have 75 or 80 drawings. We tend to bulk our drawings up with a lot of info junk, typical details and things that in many cases are completely unnecessary, just because we can, just because we have the computing power, we have the CAD systems, the technology to do it. There's a tendency to use it. Just like a race car, we want to hit the pedal once in a while and see how fast it goes. The same thing is true with all of our technology. We find ourselves using it just because we have it. And now we move into the modern day, 2010, and BIM. What does BIM bring to our design offices, to our profession, to our industry that we didn't have in ancient times? Well, I think it brings a couple of things. First of all, it allows us to build a building virtually before we build it in reality. And that's the first most important thing I think that BIM brings to our industry. We can build the entire building virtually with electronic information, electronic data, before we go to the field to build it in reality. The second thing that BIM brings is the ability to share information. We can build one model. We can all share that model, the structural engineer, the civil engineer, the architect, the building contractor, even the owner can be involved. We can share the model so that it forces or it encourages collaboration between the respective consultants and contractors involved in a project. Now, the collaboration is a very important aspect that I'll talk about here in a bit more detail in a second. But let's move now to the cost control that is also associated with BIM. This chart is fairly commonly used, I think, by people who go around and doing educational work associated with BIM. This shows the cost control or the advantages that BIM brings to a project with respect to cost control. On the horizontal axis, you see the design process, preliminary, and then construction documents, and then construction administration. On the vertical axis, you see basically time and effort, the time that we spend doing our work. The green line shows the impact of decisions that are made, and then the red line trending upward shows the cost impact of our changes. Now what BIM does is it moves the big mountain of effort that is shown in the blue line as what occurs in a traditional design mechanism. It moves it left. So the impact of our changes and the ability to impact the cost is pushed into the preliminary phase of our design, as opposed to occurring in construction documents. So whereas with traditional construction or traditional design tools and procedures, CAD basically, the mountain of effort occurs during the CD phase. With BIM, we push that into the preliminary design phase, so we have a lot more impact on the cost of our buildings and structures. These are some of the BIM models that my office has produced, CKC, a random assortment of projects. We stepped into BIM 4 years ago. We used the Revit platform. We struggled like I think most firms did when they first adopted it. The first year and a half, we had some trauma. And we had to ascend the learning curve, but we're now very conversant with it. We're big believers in it. We've actually had a couple of projects built with BIM. The building in the upper left, one building in from the upper left actually, where you see the red structural steel, that building is a Hyatt Hotel in Seattle. That was built with a collaborative model, a shared model. The building is complete, it's open. Some of the other projects are in construction. And a few of those projects actually are on either temporary hold or maybe permanent hold. We're not sure which, but they're waiting on a return to the economy. But BIM does permeate our entire industry. Now, lest you doubt the importance of the collaboration that BIM encourages, here's a chart that was produced by Stanford University, and this shows the trends in productivity between 1964 and 1998. Now, Stanford has since updated this information and taken it out to almost 2010. But this shows both a very interesting aspect of what's been occurring in the industry and also something that is somewhat troubling. If you look at the dark blue line that trends up, that is the trend in productivity in all non-farm industry in the U.S. between 1964 and 1998. So that's very encouraging. That shows that productivity was increasing in general between those years. The light blue line, though, shows the productivity trend in the construction industry, which is architecture, engineering, and construction combined. So what the light blue line shows is that there's been a very subtle trend downward in productivity in our industry. Now, there are a lot of theories as to why that has occurred, and lots of people with lots of opinions, but there seems to be a consensus on one thing, and that's that the construction industry is very factionalized. It's made up of a lot of players, a lot of consultants, a lot of contractors and subcontractors and material suppliers, and it's been increasing over the course of those 40-odd years. The number of players involved in a project has been increasing, not decreasing. We have more consultants involved. We have more specialty subcontractors involved. And as we increase the number of players, we tend to create impediments to productivity because the productivity gains that we realize with our technology are overwhelmed and even negated by the coordination nightmares that have been created by the factionalization of the design and construction process. That's where BIM can play a major role. BIM, using a shared model, encourages collaboration from day one of the process. Very, very important aspect. Talking about a couple of phenomena that I think underlie the couple of points I've been making so far, and I'll get to some projects here in a minute that illustrate some of these concepts. But the knowledge explosion that we're all part of drives the need for specialization. That's the first thing to understand. That as the knowledge pie gets bigger and bigger and bigger and continues to grow, the body of knowledge in our industry grows every day, then of necessity, any one of us has to carve out a smaller piece of the pie. So as time goes on, we all have to become more and more specialized to survive and be functional and effective in our work. But the other very important to understand is that conceptual design thinking requires broad knowledge. So on the one hand, we have the need to specialize. On the other hand, we have the need to maintain a broad knowledge base. Because if we don't maintain a broad knowledge base, then our conceptual thinking skills start to disappear. I think T.Y. Lin summed this up probably as good as anybody. He was a very prominent structural engineer for many decades, practiced out of California, but he worked all over the world. And what T.Y. Lin said was that any field of technological knowledge, such as structure, must be understood in overall terms before it can be applied with creativity at the formative stages of design thinking. So what T.Y. Lin was saying is that before you can sit down and effectively do the conceptual design on a project, which is arguably the most important stage of design, you first have to have a broad knowledge base and a broad understanding of what you do. And that broad understanding is becoming increasingly difficult to acquire and maintain because of the need for specialization. So that's something I think that as an industry we need to keep in mind in our educational systems, our offices, the need to encourage not only ourselves but other people to acquire that broad knowledge base. If you chart this out, it looks something like this, and you can argue all day long about whether they're straight lines or not, and the slope of the line and so forth. But basically, over time, knowledge is growing, which is discouraging the acquisition and maintenance of conceptual thinking skills. In fact, you could almost argue that you could take the word conceptual off of there and just say that thinking skills in general are being sabotaged by the explosion in technology. All of us can think back 20 or 25 years, those of us who are old enough, to the way we used to do things as opposed to the way we do things today. And we become habituated very quickly, if we think about that clearly and thoughtfully, we become habituated very quickly to doing things with a computer that 25 or 30 years ago we did with what's between our ears. So that's an important concept to keep in mind. Part of what we've done too in our industry is sabotaged ourselves. This picture shows in the lower left corner the Uniform Building Code, which was very dominant in the U.S. Up until the year 2000. It was the building code used throughout much of the country. The Uniform Building Code in the lower left became the Uniform Building Code in the upper left in 1997, and then that became the International Building Code in the year 2000. And we show, of course, here the 2003 edition. But here's the important thing. The book in the lower left was 5 inches by 8 inches. That became the 3 books in the upper left, which are 8.5 by 11. So the book in the lower left, which was used in the 70s and 80s, in the 90s became 3 books in the upper left. If you do a simple piece of math and compute the volume of printed material, the volume of printed material increased 7-fold. The volume of printed material in the upper left is 7 times the volume of printed material in the lower left book. Now, did our knowledge really grow 7-fold between the 80s and the 90s? I don't think so. I don't think so. But our codification process began to really sabotage our industry, in my opinion. And what that does is it creates an opportunity cost because it forces designers to spend too much time in minutia and doing things that perhaps aren't as important as other things that they could be thinking about just because the code says they have to. Now, it appears as though things got better in 2000 and 2003, except that the International Building Code actually references off a whole additional library of documents. So really, when we went to the IBC, things got ever more complex. So this concept of codification of our knowledge in structural engineering and other design fields is a real battle that all of us, I think, should fight. Building codes should be rule books, not design handbooks. They're not the playbook for the game, they're a rule book. They should be a fundamental rule book, nothing more than that. They shouldn't be a design handbook. Now, here's what happens when we take our eye off the ball and we get too caught up in the minutiae of design. This building was in Texas, constructed over the last couple of years. They got up to the 31st floor. They noticed the building was leaning. They began to study the foundations. They realized they had massive differential settlement problems. The building continued to lean. And so in December of last year, just about 8 weeks ago, the building was imploded. Now, I don't know for sure whether this was a soils engineering problem, a geotechnical issue, a structural problem. That will be determined over the course of the next few years, I'm sure. But suffice it to say that somebody involved in this project was not keeping focused on the big picture and on the fundamental concepts that are necessary to build big buildings. Now, here's a project that my office did. This building just finished up a few months back. This is in downtown Seattle, a high-rise residential tower, and just a quick description of the building. It's a cast-in-place concrete frame, dual seismic system, something we don't do very often. We did on this project because the core was split into 4 pieces. There was no central core. We had the elevator split into the 4 quadrants of the building, so we had limited shear wall to work with. So we used a combination of internal ductile frames and minimal shear wall for our seismic system. Post-tension concrete slabs using 270 KSI, half-inch monostrand. Concrete strengths up to 14,000 PSI, which is about 100 MPa. We have access to very good aggregate in Seattle, very hard granite material, and so achieving concrete strengths of that magnitude are not terribly difficult. In fact, the actual break strengths were up closer to 20,000 PSI with a concrete that was specified at 14,000. We used a reinforcing bar, a combination of 60 KSI, 75 KSI in the mat, and then 100 KSI steel for all of the seismic confinement. Because of the high-strength concrete, the 100 KSI rebar was very advantageous for seismic confinement. We have a new player in that market, by the way, now. Nucor has entered the game, one of the larger steel producers in the United States, and Nucor is now also producing a 90 KSI material, which we're using on another job in the Seattle area. The construction, I want to go back here just one second. The construction system here, we set the building up to use what's known as a column-hung deck flyer system. All of the slab forms hang off the columns, so there is no shoring, there is no reshoring. You'll notice that when you look at the uppermost level of the job, you see nothing below it. You don't see the usual 3 or 4 story stack of reshoring, and that's because the slab forms actually hang off of the columns. There's a bracket attached to the column. The slab form rolls in on that bracket. You pour the deck, you drop the slab form, slide it out, and you can actually have workmen working directly below the floor that you're pouring concrete on. Really advantageous in terms of other systems in the building that are being constructed. I take it that's my site. All right, about 1 minute. Here's a shot on the deck under construction. They're pouring the deck. You can see some of the post-tensioning cable. You can see the column forms. You don't see the column ties there because they're blocked by the column forms. Now here's what can happen again if you take your eye off the ball when you're designing with post-tensioning. This should never happen, but it does occasionally because designers have fallen out of the habit of using very simple mathematical techniques, manual techniques to compute uplift. We get involved fixing some problems of other people, and this was one where a balcony blew up that never should have because they didn't make a very quick and easy check on the post-tensioning uplift. So the final slide, going forward, what do we want to take away from this? Use our technology to simplify, not complicate, and it can do both. It can make our life wonderfully simple. It can also make our lives wonderfully complicated. Reverse the trend to over-codify. As I showed you with the picture of building codes, I think that clearly has been the case. We've sabotaged ourselves to some degree as an industry. And then finally, emphasize broad knowledge and conceptual thinking skills in addition to specialization, because broad knowledge is what underlies conceptual design. Good conceptual design is what underlies good structure. And with that, thank you for coming, and back to you, Chuck.